Okay, thank you for joining this session on physical science. We're going to be talking about section 2.3, the reading called change of state. And we're going to be looking at identifying what critical temperatures are, what latent heat is, and calculating the amount of latent heat used or released when energy changes state or when matter changes state, and then explaining how that's important for things like refrigeration and heating systems. Okay, so changes in state is going from a solid to a liquid to a gas, or from a gas to a liquid to a solid. All of those are changes in state, and they happen at critical temperatures. So every different substance has a specific melting point, and then if you add more heat energy, it has a boiling point or evaporation point. And then if you cool things down, so you have a gas and you cool it down, you take away energy, it condenses back into a liquid, and that happens at a certain temperature called the condensation point. And if you keep removing heat energy, the liquid freezes and becomes a solid, and that's at the freezing point. So we're kind of familiar with this idea mostly from water. We know that in Fahrenheit, we know water freezes at 32 degrees and it boils at 212. So that is our melting point and freezing point being the same place. Okay, so if you have ice and you add energy, when it reaches the point of 32 degrees, it'll melt and become liquid water. If you have liquid water and you remove energy, when it reaches the temperature of 32 degrees, it will turn to ice. Same thing with boiling. If you take the liquid, you add energy till it hits 212, then it would become a gas. If you have water vapor, which is the gaseous form of water, water vapor, and you cool it down, when it reaches 212 degrees Fahrenheit, it'll become liquid water. So those points are all called critical temperatures. And we're going to be dealing with them in Celsius and Kelvin instead of Fahrenheit. And as a general rule, the melting point and freezing point are at the same place. That is not true for everything. Things called amorphous solids are different, and your text talks about that a little bit. But just to kind of simplify things in your mind, those are usually in the same place, and boiling point and condensation point are in the same place. Okay, but they're different temperatures for different materials. So here are some melting points and boiling points for common materials. So table 5 is something you're going to need to remember when you have problems involving different substances. You want to look this up. It gives melting and boiling points. You'll notice it doesn't have the boiling point for everything. A lot of these metals on here do not boil at a reasonable temperature. So we know the point at which you can melt these metals, but to boil them would be millions or billions of degrees, so we just don't really even consider their boiling point. Now, generally, as you add heat energy to things, their temperature goes up. We learned that in section 2.1, and it's just kind of common sense. If you've got a fire under something, it gets more heat energy, its temperature increases. But there is an exception to that rule. At the critical temperatures, okay, so at the melting point and at the boiling point, when you add heat energy, it doesn't actually increase the temperature while the matter is changing state. Okay, so if you have ice, you add heat energy to it until it reaches that melting point, which is 32 degrees Fahrenheit, but we're using Celsius, it's 0 degrees Celsius. Now at that point, we can still add heat to it as it turns to water, but the temperature won't increase until it's become water. And the same thing at the evaporation point. Okay, it stopped raising in temperature for a while because it was changing state. Okay, so what's happening is the heat energy is being used to change the state, okay, to break that solid ice into water or to make that liquid water evaporate into a gas. The energy is used for that instead of for increasing the temperature. So the heat energy that's used for changing the state without changing the temperature, for changing the state without changing temperature, is called latent heat. Okay, so here's another way to show it. We're showing a graph where the bottom is showing energy being added, and then up the left is temperature. Okay, so if you have a solid, again, let's say you have ice that's really cold, it's below the freezing point. As you add energy, it warms up until it reaches that melting point, and then you're adding energy, but the temperature doesn't increase. Once it's all the way melted, as you add more energy, the temperature increases, and then when it reaches the boiling point, same thing. You add energy for a while with no temperature increase because that energy is being used to change the state, not to increase the temperature. And then once it's vaporized, you can keep adding energy and it'll keep getting hotter. Now, we can calculate how much latent heat there is, okay? How much energy needs to be added to make the stuff melt or boil. The amount of latent heat depends on the mass of the body and the type of material it is. So our formula is pretty simple. If we're talking about melting, you're taking the mass times the latent heat of fusion. And where do we get the latent heat of fusion? From table 6. So this is a table that has latent heat of fusion for several materials. And then for evaporating or boiling, you have mass times the latent heat of vaporization. So the words boiling and evaporating and vaporization are kind of used interchangeably. They technically mean different things, but your text tends to kind of use them to all mean the same thing because they do all mean going from a liquid to a gas. So you might see those words. So I talked about boiling point. It could also be called the evaporating point or the vaporizing point. So if we're talking about that going from a liquid to a gas, then we're using the heat of vaporization. And again, there's a lot of materials here where they don't include the heat of vaporization because it's just a ridiculous number. It's not reasonable. You can melt copper pretty easily, but to get copper to become a vapor would be temperatures that we can't even attain. Okay, so either one that you're using, okay, so if you're talking about melting something, use the heat of fusion. If you're talking about vaporizing, use the heat of vaporization times the mass, and that tells you how much energy it takes. So here's a quick example. How much energy is required to evaporate 0.0005 kilograms of liquid ammonia to vapor at the same temperature? Okay, so we're going from a liquid to a vapor. So we're going to use the heat of vaporization. And our formula is really simple. To find the energy, you just take mass times that number. We get our number from this table. So we're looking at liquid ammonia. So ammonia going from a liquid to a gas, we want vaporization. So we just take that number times the mass, which we got from our problem, 0.005 goes here. Oh, I am sorry, I used the wrong number. So I did the heat of fusion. Oops. Okay, so that's not right. I'm so sorry. So we would take this mass times this number over here. So that's going to give us a much bigger number. I apologize. So we should have 0.0005 times 1368542. All right, we'll look at a different example then. Hopefully this one I did correctly. I'm sorry. How much heat energy must be applied to melt 5 kilograms of lead at 20 degrees Celsius? So we have a problem here. We're talking about melting lead, all right, but you don't melt lead at 20 degrees Celsius. This is room temperature. Okay, at room temperature, lead is definitely a solid. So we have to do two steps, two different calculations. The first one is actually just heating the lead up. How do you get from 20 degrees Celsius to its melting point of 327 degrees Celsius? Okay, and then the second step is finding the latent heat. So let's look at how we do all that. So again, if you look back at table 5, the melting temperature of lead is 327. So we're going to do the two steps here. So our first step, we've got to take that lead from 20 degrees Celsius up to its melting point of 327. To do that, we need to think of this formula that we got in section 2.1. Okay, this is just how much energy it takes to heat stuff up. Our formula was Q, which is energy, equals 4187 times the mass times the specific heat times the change in temperature. So we get our specific heat from a table that was back in that section, table 2. We're dealing with lead, so our specific heat is this number. So we put all our numbers into that formula. So this stays the same. Our mass was 50. Our specific heat we got from the chart. And we have our final temperature and our starting temperature. All right, so this is how much energy it takes just to heat lead up to its melting point. Okay, our next step is finding the actual energy used for the latent heat of fusion. So that was just mass times latent heat. So our latent heat of fusion for lead is 22,770. So we take the mass times that number, and this is our energy to melt it. So here is the energy that it takes to heat it up to the melting point, and here's the energy that it actually takes to melt that much lead. So we just add those two together, and there's our total answer is 3,130,884 joules. And we could divide that by a million to get 3.13 megajoules. So how do we know what we're doing on the exam? So we've got kind of three different ways to talk about changing heats and melting and changing temperatures. So you got to kind of pay attention to what temperatures are given. If you have a question on your exam that says you're melting something at the same temperature, or it says the material is at its critical temperature and you're melting it or you're evaporating it, then it's easy. You just take required energy is equal to the mass times the latent heat. That's how much energy it takes to melt it. If it gives you a starting temperature and then says it changes state at a critical temperature, so just like our lead, it started at 20 degrees, it melts at 327 degrees. Then you have to do two calculations. First, find the amount that it takes just to heat the lead up, then the amount that it takes to actually melt the lead. Okay, and then sometimes you'll see questions that it doesn't talk about change of state, just heating or cooled. Okay, you've got a block of copper and you're heating it up this much, how much energy does it take? It doesn't say anything about melting or evaporating or freezing or condensing. So then you just use this formula that we got from section 2.1 to find out how much heat energy it took just to heat it up. So we've been talking about the latent heat involved in melting and evaporating, but it works in reverse too. So if you have a vapor and you cool it down, so to cool it down, you're taking away energy. It keeps losing energy, the temperature goes down until it reaches the condensation point. Okay, so that's the point where the water or the vapor becomes a liquid. So you can think of the dew point outside where the water vapor in the air becomes a liquid and you get dew droplets on the grass and the cars and everything outside. So at that point, it could still be losing energy, but the temperature doesn't decrease. The temperature stays the same while it goes through that change from a liquid to from a gas to a liquid. Okay, then as you take away energy, it continues to get colder till it reaches that freezing point. So now we have a liquid, and you take away energy, the temperature doesn't change while it freezes. So it goes from a liquid to a solid, releasing energy without changing temperature. And then if you take that ice and you cool it down even further, or you take away more energy, it will cool down further. So with heating things up, it's using energy to change state. With cooling things down, it's releasing energy to change state. Here's a question using that. So how much energy is released when 0.002 kilograms of ethyl alcohol vapor is condensed to a liquid at the same temperature? So we've got ethyl alcohol. It's being condensed, and it says at the same temperature. So that's our clue that we don't need to do additional calculations. We're just right at that critical temperature. All we're talking about is how much heat does it lose when it changes state. So we've got ethyl alcohol. Okay, here's its heat of vaporization. And it's called heat of vaporization, but it's also the same amount of heat that's released. You've also got heat of fusion, which is the amount of heat released when something gets colder and freezes, but that's also the same amount of heat that it takes to melt. So they just use one word even though it works in both directions. Okay, so we got heat of vaporization times the mass, and that tells us how much energy is released when it goes from a vapor to a liquid. Okay, so we get the idea as you go from a liquid to a solid, energy is released. As you go from a solid to a liquid, energy is taken, okay, it uses energy. And that energy is usually just in the form of heat. So why does this matter? Well, this is how your refrigerator works, and air conditioner and heating and everything. Changing states from a liquid to a vapor takes heat energy, and it's got to get it from somewhere, so it soaks it up from its surroundings. It takes it from the air. Okay, so you have refrigerant, which is just a liquid that runs through the pipes outside your fridge. So the liquid refrigerant comes from outside the fridge. It goes inside the fridge. And inside the fridge, I mean like in the walls of your fridge. You can't actually see it. Hold on. There we go. So it goes into the walls of your fridge and it vaporizes. Okay, it's allowed to go from a liquid into a gas. And when it does that, it has to soak up heat energy from its surroundings. Well, its surroundings is the air inside of your refrigerator. So as it goes from a liquid to a gas, it sucks out heat energy from your refrigerator. Okay, then that gas travels through and then goes out. And then behind your fridge or in back of it, there's a compressor that squishes that gas back down into a liquid. And as it does that, it releases heat energy. So that's why you could feel warm air behind your fridge or under your fridge. And then it just goes through that whole process over and over. That liquid goes into your fridge, and then right here, it becomes a gas. And to do that, it takes heat energy from the air around it. So it makes cold air inside your fridge. And as it does that all day, it's continually making sure the air inside your fridge is cold, keeps the food in your fridge cold because it's taking the heat energy from them to turn into a gas. Okay, and I focused on a refrigerator, but this is also how an air conditioner works. And a heat pump works the same way, just kind of focuses differently. So it wants to warm things up. So the part like inside of your house where you want it to get warm, that's where the compressor is that makes the um, liquid, no, makes the gas turn into a liquid and it releases the heat into your house. Outside the house, it would allow the liquid to turn into a gas and take heat energy from the surroundings. And the last thing they talk about in this section is pressure's effect on changes in state. So if you keep a liquid under high pressure, it's harder to boil it. It doesn't boil at the same temperature. And this is why a pressure cooker works. So you have a liquid, water, and that normally boils at that normally boils at 100 degrees, but because it's under so much pressure, it reaches 100 degrees and it can't boil. The pressure keeps it still as a liquid, so it can get hotter than that. So you could have it to be 120 degrees and it's still liquid. And the point is that you've got this hot water in there, it's going to cook your food faster at 120 degrees than it would at 100 degrees. So the pressure just keeps it as a liquid so that it can cook your food faster. And a car's radiator works the same way. It keeps that liquid under pressure so that it's forced to stay as a liquid. And that brings us to the end of this section. If you have any questions, don't hesitate to contact your instructor.